Hi and welcome to John's Maths book. In this video we're going to be looking at Taylor series approximations. If you like the video then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. A Taylor series is a polynomial expansion of a function and approximates that function about a region at a point x equals a, where a is not equal to 0. At a equals 0, it's known as a Maclaurin series. The function needs to be infinitely differentiable, which means we need to be able to find the first, second, third, and so on derivatives of the function. The function also needs to be defined in the region x equals a. Why do we use Taylor series, I hear you ask? Well, they're used in computations of functions that are difficult to compute directly. For example, your calculator may use a Taylor series to approximate sine or cosine, etc. The long form of the Taylor series expansion is shown on the board. Note the higher degree of polynomial we use, the higher the accuracy. The shorter form of the Taylor series is shown here, where the function f of x is approximated by the sum from n equals 0 to n equals infinity of the nth derivative evaluated at a divided by n factorial and multiplied by x minus a to the nth power. Let's now take a look at an example of how this works. We want to approximate the function e to the power of 2x using the second order Taylor polynomial about x equals 1. This red line is a graph of y equals e to the power of 2x. The vertical line, shown in purple, is x equals 1 and shows the point about which we want to approximate the function. To approximate e to the power of 2x about the point x equals a, our second order Taylor series polynomial will be created when n equals 2 in the formula. This will give us the function evaluated at a plus the first derivative of the function evaluated at a divided by 1 factorial and multiplied by x minus a plus the second derivative of the function evaluated at a divided by 2 factorial and multiplied by x minus a all squared. Let's start by evaluating the first term, f of a. We know that f of x equals e to the power of 2x, so when x equals 1, f evaluated at 1 gives us e squared. Next, let's look at the first derivative of f evaluated at a. F prime of x equals 2e to the power of 2x. So f prime evaluated at 1 gives 2e squared. Looking at the second derivative of f evaluated at a, we see that the second derivative of f of x is 4e to the power of 2x. If we evaluate this at 1, we get 4e squared. If we plug these terms back into the Taylor series equation, we get e to the power of 2x is approximated by e squared plus 2e squared multiplied by x minus 1 and divided by 1, as 1 factorial is 1, plus 4e squared multiplied by x minus 1 all squared divided by 2 factorial, which is 2. Expanding this out, we see that e to the power of 2x is approximated by 2e squared x squared minus 2e squared x plus e squared. If we now go back to our graph of e to the 2x and plot a graph of the second order Taylor series polynomial around the region at x equals 1, we see that at x equals 1 we have a very good approximation, and in this case it's exact. In this second example, let's look at approximating log of x about the region x equals 2 using a second order Taylor polynomial. So for this approximation, we'll be evaluating the function at a plus the first derivative of the function at a divided by 1 factorial and multiplied by x minus a plus the second derivative evaluated at a divided by 2 factorial and multiplied by x minus a all squared. So first, let's start by evaluating this term here, f of a. So f of x is equal to the log of x. So when x is equal to 2, the log of 2 is equal to 0.6931472, and that's rounded to 7 decimal places. So now let's evaluate f prime of x at x equals a, where a is 2. So the derivative of f of x is 1 over x. So if we evaluate this at the value of 2, we get 1 divided by 2, or a half. And then looking at the second derivative of f, evaluated at a, we see that the second derivative of f is minus 1 over x squared. So if we evaluate that where x is equal to 2, we get minus 1/4. Now if we plug all these values back into our second order Taylor series approximation, we get the log of x is approximately 0.6931472 plus a half times x minus 2 minus 1/8 times x minus 2 all squared. And expanding this out, we get our quadratic approximation to be minus x squared over 8 plus x minus 0.8068528. Here's the graph of log x in red. The black line here shows the region on the graph where x equals 2. And now graphing the Taylor series second order approximation that we just calculated, we see how close an approximation it is in the region of x equals 2. Here, when rounded to 5 decimal places, it's exact.